Hello, my name is Philipp Russmann. I'm working at the research center in Jülich, and I'm the main developer of the AiiDA-KKR plugin, which connects our KKR code uh, to the AiiDA world. So, what is KKR? KKR is a density functional theory implementation, and a special implementation since it directly gives access to green functions and not the wave functions that probably most of you are familiar with. So instead of solving for the eigenspectrum of this Hamiltonian H, we solve for the green function. And then the central properties are all included in this green function. For example, for the DFT, we need the charge density n, which we can simply calculate by taking the imaginary part of the green function and integrate up to the Fermi level. All this is implemented in our UKKR code package, where you can find more information here. And more general information about the KKR method you can find in this review paper down here. So this is an all-electron method that has, due to having access to the green functions, some special properties. Suppose we now have the electronic structure of a crystal that we want to describe, and then we want to look at defects into this in the system. We can embed an impurity into the system by using this Dyson equation. Here, G0 is the green function that we have pre-computed, the green function of a perfect crystal into which we want to put our impurity. And then we embed the impurity into the system by just considering the change in the potential due to the presence of this impurity locally around the defect in a real space cluster and solve this Dyson equation. Now I want to stress that this does not need supercells, but just this small real space cluster around the impurity, which is then very efficient, in particular if you have a large unit cell to start with. And this gives even access to transport properties or other unusual features that other codes cannot access as easily. All of this is included in the AiiDA-KKR plugin, and I want to discuss this now in more detail. So a few facts and figures about the AiiDA-KKR plugin. Currently, the paper we wrote is under review. You can find a preprint on arXiv. The source code is on GitHub and documentation on Read the Docs. It runs with the current AiiDA core versions. Everything above 1.0 should work, and it's very easy to install. It is uploaded to PyPy, and you can just download it from there. The basic idea is that we need to perform different calculations that this UKKR package provides. In particular, these are the Voronoi, KKR host, and KKR imp, which I will come to in a moment. Overall, there are several workflows implemented in AiiDA-KKR, and still some under development. And this is a modular design. They build on top of each other, and in this talk I will just show you the top level workflows, which makes it easy for the user to use our code. Additionally, we have programmed some tools like the plot KKR method, which is a convenience function that can take all the different nodes that AiiDA-KKR provides, like a workflow node or a calculation node, and generate a standard plot out of this. And this we will use later on in the rest of the talk. So how can you do an impurity embedding calculation? The target is we want to solve this Dyson equation. So we actually have to do two steps. First, we have to find the G0, our green function of the perfect crystal into which we want to embed our impurity. And then in the second step, we need to embed the impurity into the system. So this can be done like this. We start with an AiiDA structure. This can be a bulk structure, a thin film, or even a semi-infinite system, which is another specialty of having green functions and not wave functions to deal with. And then the Voronoi code needs to be called. The Voronoi code in the KKR method sets up the system. It prepares all the calculation, and in particular, it generates a starting potential that we need for the KKR host calculation to run. The KKR host calculation then performs the self-consistency cycle, and eventually after convergence we get our G naught out of this. To then embed an impurity, we need to define the position and the kind of impurity that we want to put in. This is some impurity info node. And this is then used to actually write out this G naught in the real space cluster that we need, which is then the input for the impurity calculation that we want to do in the end. So in the following, I want to show you an example, and in particular, I want to show you how to use the plugin at the example of these top-level workflows that I mentioned before. All of this, the Voronoi, the KKR host calculation, and the convergence, this is done by the KKR SCF workchain. And then in the second step, we use the KKR imp workchain to write out the green function of the host system and then embed the impurity by running the KKR imp code. So let's take a closer look at the KKR SCF workchain, which takes just a simple structure and some settings as inputs and then converges the system. So internally, you perform a Voronoi calculation. There are some consistency checks and error handlers implemented that take care of common mistakes. And actually, several steps of KKR calculations can be run. In particular, we often do a pre-converging with a lower accuracy set, which is faster, and then finally converge it in a higher accuracy setting to reach the final answer that you're interested in. So this has a lot of different features internally, but we have defined a lot of sensible defaults that makes it easy to use, but fully customizable if you want to change some of its behavior. Let's take a look at a concrete example and look at a simple system of bulk FCC copper. We can simply submit the KKR SCF workchain with AiiDA's submit command. We just have to provide the Voronoi code, an instance of the KKR code, and some basic parameters. With this parameter, we can, for example, set how accurate our calculation should be, or if you want to do a spin resolved or paramagnetic calculation. And of course, we have to give the AiiDA structure, which I have prepared for this example. The second step is then to embed the impurity into the system, and this we want to do now for silver impurity in this copper FCC host. Here we reuse the pre-converged system to write out our G naught of the host system in the impurity cluster that we need. And this gets information from this impurity info dictionary node that contains the information on the position, etc. of the impurity that we want to run. And then also here in this step of the impurity calculation, we run a series of KKR imp calculations to finally reach convergence in a robust way. So this looks very similar, submitting such a job. And I want to draw your attention to this impurity info node. Here we define the type of impurity. We say our nuclear charge is 47, which is silver. And we define a cluster radius here 4 angstroms, which is the silver atom here in this copper matrix, and the first 2 shells of neighboring copper atoms around it. And here in the last line, we also connect to the previous result of the KKR SCF workchain and link here the output of this workchain. So how does such a result of a calculation look like? To visualize this, I did an additional step after the self-consistency of the impurity. I used the KKR imp DOS workchain to compute the density of states of this impurity system, and this you can see here on the right. The red line is the density of states of the silver impurity, where you see here a resonance in its density of states coming from the D states of silver. And the blue lines here are the first and second copper neighbor in the crystal. And you can clearly see that here in the first copper neighbors around the silver impurity, there's a strong hybridization in the electronic structure, and this leads to the appearance of this peak that is absent then for further distances from the impurity. To illustrate how complex the full calculation actually is, I put in here an export of the AiiDA graph that you find from the AiiDA database. Here, the different colors of the nodes are data nodes, which are, for example, the input structure or input and output dictionary nodes of calculations. Logical nodes, which are workflows or calc functions, and actual calculations like Voronoi, KKR host, and KKM calculations. Now, I showed you that AiiDA-KKR makes it much easier to use the KKR code, but we can also go towards the high throughput idea of AiiDA and actually do multiple impurities. Here also this impurity problem is a nice way to use this, because we can actually reuse the G0 for several impurities and then look at chemical trends, varying the impurity and investigate this in detail. So here I again shows a mini example of now magnetic impurities in the copper host. So we can submit all these calculations simply with a loop over the nuclear charge for 3D impurities, and then we submit all these KKR impurity work chains. Here on the right, you see then the final result, where I chose to plot the impurity minority density of states for chromium up to cobalt, where you can clearly see that with the going through the D series of the elements, you get an increased filling of this minority density of states. So here you see this line of the Fermi level goes through this peak in the minority density of states. Of course, we cannot only look at a simple impurity, but we can make it more complex and put two impurities close to each other. As it is illustrated here, we can place two impurities next to each other or at larger distances. And this we did with our magnetic impurities. We kept the first impurity to be fixed and varied the second impurity in the type of impurity, going from vanadium to cobalt, and also in the distance between these impurities. And here on the right, you see then the results or the influence this has on the impurity spin moment. The gray line is always the single impurity value, and then these different colors show you how the impurity spin moment converges towards this single impurity value if you increase the distance between these different impurities. But for nearest neighbors, you actually see a strong influence on the magnetic properties of this iron atom. And the same thing you can investigate in the second impurity, where you can also nicely see the evolution of the spin moment with the increasing defilling in this transition metal series. Another special property of the green function method is that we can calculate exchange coupling constants. Suppose we have two magnetic impurities in our system and we want to find out how strongly do they interact. Then we can map this onto the Heisenberg Hamiltonian, and having access to green functions, we can actually compute these exchange coupling constants quite easily. You see here the green functions appear, and some T matrix which is connected to the potential of these impurities in this example. So this gives us direct access to these properties and even allows to extract complicated things like the Jaroszynski-Moria interactions, and all of this can then serve as input for micromagnetic simulations, for example in the Spirit code that is also developed in Jülich. So here's an example result, how this can look like. I showed you again these dimers of impurities, so keeping the first atom is iron and varying the second impurity here now for the first two neighbors. And the different colors here show the effect that different second impurity has on the exchange interactions. You can clearly see this chemical trend where the exchange coupling constants vary strongly in their size and even change sign once we go through this minority, the filling in the minority density of states that we have seen earlier. So what's the future of the AiiDA-KKR plugin? Well, we will have several more features of the UKKR code package, which are not included or not connected to AiiDA-KKR at the moment. In particular, we can also then do transport calculations, for example, Boltzmann transport calculations that take into account the effect of these impurities that I discussed earlier. Can then, for example, look at the spin orbit torques that several impurities can exert. And at the moment, we're also implementing superconductivity via the Bogoliubov-de Gennes equation into our UKKR code, and it is planned to also make this available through the AiiDA-KKR plugin in the future. We can compute STM images with the quasi-particle interference technique, which gives you such an image, and this might be very useful for experiments to identify the effect or the signatures of different impurities at surfaces, for example. And finally, we want to also do more dynamical properties, get access to spin excitations and magnetic fluctuations, which is possible right now with the UKKR package, but not within AiiDA-KKR yet. And eventually, we also want to directly feed our exchange coupling constants back to Monte Carlo codes, for example, the spirit code directly within AiiDA. Last but not least, I want to acknowledge, of course, for funding and computational support that all this development was accelerated with. And I want to thank you all for your attention.